We'll now look at the idea of linearly independent and linearly dependent vectors. Let's consider this equation x1a1 plus x2a2 all the way up to xn an equal to 0, where our a's are vectors and the x's are some scalars. We say these vectors are linearly independent if this equation has only the trivial solution. So the only way for this to work would be all of the x's equal to 0. Otherwise, we say they are linearly dependent. So let's look at some examples. Here are 3 vectors, and I want to know if they're linearly independent or linearly dependent. So essentially, I need to put them in a matrix and row reduce. Since we are specifically looking to see if this is equal to 0, our last augmented column will just be all zeros, so I'll ignore this the same way we did with homogeneous systems. So here's my matrix. I need to row reduce it and see if I have only the trivial solution or if I have infinitely many solutions. And when I try to reduce this to row echelon form, this is the matrix that I get. We can see that there's no free variables since I have a pivot in every single column, which tells me that I have only the trivial solution. So these vectors would be linearly independent. A lot of times we can look at the set of vectors and determine if they're linearly independent or dependent with no work, no row reduction. So let's consider each of these special cases. Let's start with the case of just a single vector. We want to know if a single vector is linearly independent or dependent. That means that we're looking at this equation, x1 times a1 is equal to 0. If this is linearly dependent, that implies that there's a non-trivial solution. And a non-trivial solution means that x1 might not be 0. x1 equal to 0 is absolutely a solution, but if we have a non-trivial solution, there is definitely a solution where x1 is not equal to 0. That would imply that a1 is equal to 0. So this tells us that this is only dependent if our vector is just the 0 vector. So if we have the vector of all zeros, it will be linearly dependent, and if it's any other vector, it will be linearly independent. And we can actually expand this idea right here using more than one vector. So the expansion of this, if the set of vectors a1 through an contains the 0 vector, then the set is linearly dependent. So let's try to prove this. We know this set contains the 0 vector, so let's reorder it so that the 0 vector is a1. Now let's consider this equation. a1 plus 0a2 plus 0a3 all the way up to 0an is equal to 0. Well, this is a non-trivial solution. So since we have a non-trivial solution, we know that this set is dependent. Next, let's consider the case of 2 vectors. In this case, I'm considering x1, a1 plus x2, a2 equal to 0. Once again, this is dependent if it has a non-trivial solution. That means it's dependent if either x1 is not equal to 0 or x2 is not equal to 0, or both. So for now, let's assume that it's x1 that's not equal to 0. Then I can rewrite this as a1 is equal to negative x2 over x1, a2. So in this case, they would be dependent if one is a scalar multiple of the other. The other case that's easier to see, if a set of vectors a1 through an contains more vectors than there are entries in each vector, the set will be linearly dependent. Since the set a1 through an has more vectors than it does entries, we know that when we form the matrix A from these vectors, that we get an M by N matrix where N is greater than M, since we have more vectors than there are entries in each vector. This means I can have at most m leading entries in the rows. So if I reduce this to row echelon form, I can have at most m leading entries. This means that every column is not a pivot column. And since every column is not a pivot column, we have to have free variables. Since we know we have to have free variables, that means that ax equal to 0 has a non-trivial solution. And if it has a non-trivial solution, then that means our columns are dependent. So let's consider these two vectors here, 2, 4, negative 6, 10, and 5, 10, negative 15, 25. We want to know by examination if these are independent or dependent. And we should notice that if I multiply the first one by 5 over 2, I get the second one. Therefore, these will be linearly dependent. Here I have three vectors, and once again, I want to see if they're linearly dependent. And this time, I can see that I have the 0 vector. And any set of vectors that contains the 0 vector is going to be linearly dependent. Now let's consider these 4 vectors. So we should see that we have 4 vectors and 3 entries. In this case, the number of vectors that I have is larger than the number of entries. So that tells me that these are linearly dependent. So now let's look at a couple of properties. First, the columns of a matrix A are linearly dependent if and only if Ax equal to 0 has only the trivial solution. So let's try to prove this. Let's suppose the columns of this matrix A are linearly independent. So this tells me that the equation x1 a1 plus x2 a2 all the way up to x and an equal to 0 has only the trivial solution. So we know that ax equal to 0 has only the trivial solution. So now we've done half of it. And the other half is going to be very similar. We suppose ax equal to 0 has only the trivial solution, which means this equation here can only have the trivial solution, which means by definition they're linearly independent. Our next property, a set a1 through an of 2 or more vectors, is linearly dependent if and only if at least one of the vectors can be written as a linear combination of the others. Let's start by supposing they are linearly dependent. If they're linearly dependent, that means this equation x1, a1 all the way up to x and an equal to 0 has a non-trivial solution. That means at least one of these x's is not 0. So we'll reorder them so that x1 is not equal to 0. If x1 is not equal to 0, I can solve for the vector a1. I get a1 is equal to negative x2 over x1 times a2, negative x3 over x1 a3, etc., all the way up to minus xn over x1 an. So now I've written this as a linear combination of the other vectors. And I'm not going to prove the other direction. I encourage you to try it yourself.